I think we know each other for many years. And we started our cooperation with Dr. Abramow, myself, and Vince from Penn State. Vince has been working for more than 30 years, mostly for the government, only for the government.
Only for the government.
Nuclear Regulatory Commission, Idaho National Laboratory, Los Alamos National Laboratory, and now he's at Sandia National Laboratory. He has published more than 30 peer-reviewed journal publications, and his area of interest is nuclear reactor safety, thermohydraulics, linear and nonlinear solvers, and verification, validation, and certainty quantification. He has been a adjunct professor at NC State, but also University of Florida, Penn State, Oregon State, University of Idaho, and Texas A&M.
And University of New Mexico, I forgot that one. So, I think I came out here a year or so ago to talk about the overall philosophy of MELCOR. Now I'm going to talk a little bit more about actual nuts and bolts, how I'm building the software. So that's what I mean by implementation. Overall outline, I'm going to have some background information. I'm going to talk about Tailor series, which is the heart of all of the numerical methods we use. I'm going to introduce a concept which is different, and that is a set of generic equations which I believe will allow me to describe very complicated physics with a very small set of unique equations. I'll then discuss accuracy and an idea that, and I don't know, Robert always gets credit for Matryoshka, the name, but I think I came up with it. The idea is Matryoshka, which is the little Russian wooden dolls that are nested, that fit inside of each other. And the idea is we want to build software that has multiple levels of fidelity so that depending on your application, you're using the correct level of fidelity for the problem you're solving. The main one that I've been working with a lot of the students that I've been doing is we are driving the bus, we're not riding the bus. We're the ones who are writing these codes and figuring out what the physics models are. We should aggressively be choosing what physics we need to model, how we need to model it, and what numerical approaches we're going to use to model it. Active, not passive. So, background. I talked about this before. 5 main components to MELCOR3. The 3 Matryoshkas. There we are. Physics Matryoshka, which means different physics models. Two-phase flow, we can use 3 equations and have a homogeneous equilibrium model. Relap 5 uses 6 equations. Liquid vapor, Cobra uses 8 equations, liquid vapor droplets. But they're all modeling two-phase flow. We can make a single code with all those models in it. Geometry Matryoshka. The idea here is that some problems, a simple lump parameter 0D description of what's happening is plenty accurate enough for what you're doing. Other problems need full 3D. So, building a single code that has multiple levels of geometry. Solver Matryoshka is the idea that we're going to make our matrices larger if we can take big time steps, and smaller if we can take if we have to take smaller time steps. In a severe accident, if I am modeling detonation of hydrogen, I don't need a big matrix. I'm going to be taking time steps that resolve the sound scale of the hydrogen detonation, and that means a diagonal matrix is plenty accurate enough. If I'm modeling Fukushima, which stretched out over 3 weeks, I need to have a fully implicit code which will allow me to take time steps that are on the order of an hour or 2. So again, the idea is put in multiple choices for geometry, solver, and physics, and be able to choose the one that's appropriate for what you're doing. The two main concepts that go along with this is that you need to understand what your error is. So we're going to have time step control that controls the amount of error that we're getting in our time integration scheme, and we're going to have mesh generation, which determines the nodalization size to give us the accuracy and speed that we require. In Cobra, Trace, Track, Relap, Cathar, Athlete, the student using the code is required to define the nodalization that they're going to solve the problem on. I don't think that's a good idea. I think the person who wrote the code knows better how to choose that, and that the user of the code should describe the transient, the geometry, and the initial conditions, but other details should be left to an algorithm. I'm going to make some statements about physics in MELCOR3 which seem obvious, but in all thermal hydraulics codes I've worked on over the last 30 years, the physics doesn't have timescales. Things change instantly from one time step to the next. Whether that time step is or whether that time step is a millionth of a second, things change across one time step. That's just bad physics. All physics have length scales. Again, the same idea in our current codes is that physics change from one control volume to the next control volume. Whether that control volume's 10 meters long or 1 millimeter long. They don't build the physics of the length scales and time scales into the code. We then want to have a key concept, and the idea of this matryoshka is that you need all the important physics resolved and all of the unimportant physics removed. A good example of this is sound waves in a reactor. Yes, you have noise in the reactor and there's a little bit of sound, but you don't need a code that tracks all the sound waves in a nuclear reactor because they're unimportant. So, you remove the unimportant physics from your simulation. Again, this seems obvious, but no current thermohydraulic codes conserve mass. They all lose mass in a transient. There's none of them that even come close to conserving momentum. They try to do conservation of energy, but if you remember, total energy is kinetic energy plus internal energy. If you don't conserve momentum, you can't conserve energy. This is a key concept that everyone was taught in undergraduate, that all physics have increasing entropy. And almost none of our simulation codes have increasing entropy. The idea is that things should diffuse with time, not artificially sharpen up. There's two concepts, and I was just talking about this with Nam and his group, is the idea that there are conservation of mass, momentum, and energy. These are the key concepts that determine the safety of the reactor. There are secondary concepts of fluxes. If I have the flux of mass wrong, I have the correct amount of mass, but it's in the wrong place. So, doing a flux wrong is a much smaller error than losing or gaining mass. It's the same concept for exchange terms. Boiling, condensation, wall friction, wall heat transfer. None of these processes create mass, momentum, or energy. They only move their location. So, conserving mass, momentum, and energy is the first choice. How and where they're located is a lower priority. I'm now going to talk about a concept that's very simple, but a lot of people don't remember. Way back in your first semester of calculus, you went over Tailor series. And all of our codes are based on first order Tailor series. Nothing more complicated. I have my value. It's linearized about a point based on a derivative and higher order terms. If I take that Tailor series and rearrange it, that's how we do finite differencing of time integration. If I write the Tailor series in space instead of time, I can rearrange that Tailor series, and it's how I approximate a spatial derivative. So, I have the derivative I want, I have my numerical approximation, and then I have the error that I made when I was trying to make that approximation. This is basic process. So, when you're asked to control volume size, your job is to set the mesh spacing. What you're setting is the size of this term. Did anyone ever tell you when you're choosing your control volumes or your nodalization that that was the term you were setting? No, but that's what's setting the error based on your nodalization. I'm going to base MELCOR3 on Newton's method. And one of the things when I worked at Los Alamos, they left me in a dark basement for about 10 years to think about things. And one of the things I discovered was every numerical method that I had been taught through my career, I worked backwards and realized it was a subset of Newton's method. So I am comfortable that when I do Newton's method in MELCOR3, I'll be able to capture all of the solution algorithms in COBRA, Trace, Track, Cathar, MELCOR, and all the codes that were its predecessors. Once again, we write out a Tailor series and to calculate a state vector x such that the residual is 0. And when I say residual, I mean conservation of mass, momentum, and energy. Those are my residual equations. I'm looking for a state space, densities, velocities, and temperatures that drive my conservation of mass, momentum, and energy to be 0. And what we find is, once again, we write out a Tailor series. This time, though, the Tailor series in Newton's method is in terms of the state vector, densities, temperatures, pressures, velocities, not time or space. But it's the same Tailor series. We do some minor rearrangement, and what we see is that Newton's method has an error term that scales with the square of the change in state space. So the idea, you will always hear people say Newton's method is a second order method. It's because that error term is the square of the change in state space. I was talking with Paulo this morning about a way to do solving of matrices, and what you can do, and this takes a little while to get used to, you can actually solve a matrix faster than you can build it. And that is a very interesting way to run your code. And you accomplish that through a Jacobian-free approximation. The idea is I don't need to build the Jacobian matrix to approximate the Jacobian matrix times a vector. What I can do is Jacobian matrix times a vector simply by evaluating my residual functions. So if I can get the effect of the Jacobian matrix times a vector, if the number of matrix vector products I need to solve my matrix is smaller than the amount of work I needed to build the matrix, I can actually solve my matrix faster than I could build it. One of the key parts in all thermal hydraulics codes is we have these big, ugly equations of state for steam, water, and they have a variety of different approaches, and they're ugly and nobody really knows what they are. But inside of every code, there's a linearization of the equation of state. That linearization is a first-order Tailor series. This time we're taking, for example, a Tailor series for density in terms of pressure and energy. And we get the standard Tailor series approach. But what we now see are the second-order terms that come from a Tailor series approximation. So, all the numerics in MELCOR3 will be based on a first-order Tailor series approximation. In every one of these slides, every time I wrote down the approximation I was going to use, I knew exactly what the error was. So, what we're going to do is now we know that our numerical methods are based on a first-order Tailor series. Well, the way to describe that is a first-order Tailor series is a straight line. We're going to approximate our answer with a straight line. And that approximation is accurate if your answer is almost a straight line. So, the trick is to choose the mesh spacing and the time step such that however complicated our solution is, when we look at a small piece of it, that small piece looks like a straight line. So, if it looks like a straight line, using a straight line to approximate it is accurate. So, everything then becomes based on choosing our mesh spacing and our time step so that it does look like a straight line. The key concept that goes into recognizing that we're going to use a straight line to approximate things is the smoother the function in time or space, the easier it is to approximate it with a straight line. However, if you have a process that says nothing happened on the last time step, and now I have a discontinuous step change on this time step. A good example in thermal hydraulics. I was horizontally stratified flow in the last time step. The next time step results in about a 3 to 4 order magnitude difference in the frictional factor. If you have a discontinuous change, no straight line can approximate a discontinuity. It's going to be wrong, and it's always going to be wrong. But if you have a smooth function, something that changes gradually in space or time, it's easy to approximate with a straight line. So, one of the key things that we want is to get smooth functions. If we add entropy to a function, it makes it smoother. if we remove entropy from a function, it makes it less smooth. And we remove entropy with bad numerical methods, discontinuous changes in models, unstable numerics. All of these are approaches that remove entropy. So, from the beginning, we want our physics to be entropy increasing. So, no discontinuities, no point sources. A point source is a sharp change in both space and time. We want things to grow gradually and gently. The other thing is what is often happening, and a set of friends of mine did this, and it just broke my heart. They went through and spent a huge amount of time building these beautiful models that all solved increasing entropy physics models. And it's like, great. And then they turned around and used unstable numerical methods on them. And it's like, oh, all that work you just did in your physics model, you just threw away in your numerical method. So what you have to have is numerical methods that increase entropy and physics models that increase entropy. So what you need for numerical entropy increasing are stable numerical methods. Anything that oscillates on every other time step is creating structure from nothing. It's decreasing entropy instead of increasing entropy. And the way you notice discontinuities in your code is the if tests. If your code says, if Reynolds number is less than, I'm laminar and use this correlation. If Reynolds number is greater than 2300, I'm turbulent, use this correlation. Then what you've done is created a discontinuity at 2300. Which means because of a round off bit, I calculated 2299.99, and that's a completely different physics than 23001. That's absurd. Your models should not have step changes and discontinuities in them because all of our numerical methods are trying to approximate them with straight lines. And you can't approximate a discontinuity with a straight line. One of the things that is controversial, and my neutronics friends, I'm sure will take offense at this, but they'll get over it. One of the things that is a flaw in the way that we are teaching students is you're taught to think of things as partial differential equations. And when we write simulation codes, we're writing simulation codes to solve partial differential equations. I'm writing simulation codes to model reality. I'm not writing codes to solve partial differential equations. There's a subtlety there that's important. When you think about back in your fluids class, when you were deriving the fluid equations, the instructor stood up and said, first we're going to take a box and we're going to see how much mass fluxes in and out of this box. Then we're going to let the size of that box go to 0. And when we let the size of the box go to 0, we can write a partial differential equation. Then we're going to apply a numerical method to the partial differential equation. So the first thing we're going to do is take that box of size 0 and create a delta x for the box size. So we started with a finite size. We let that size go to 0, and then we turned around and then spread that 0 size back out. Well, there was no point in that. Start with a finite size and stop. You have a box, you can write how much flux is in, how much flux is out. The change in my controlled quantity is the sum of the fluxes into the box and the sum of the fluxes out of the box. And the sources or sinks in the box. That's a simple equation, and it conserves mass and energy. That's two of the three main things we need to do in a code, and it's described by a single equation with a simple idea of control volumes and flow in and out of control volumes. Fluxes include both advective and diffusive fluxes. So we can do heat transfer, we can do neutron diffusion, but in neutron diffusion, we're conserving the number of neutrons by having diffusive fluxes in and out of a box, plus the number of sources that come from the fission. So this equation conserves mass, energy, neutrons, whatever it is we need. We are going to be careful about describing our source terms. We're going to partition our source terms into two types of source terms. And for lack of a different terminology, I'm going to call them internal. An internal source term is boiling. The mass in the water moves and becomes mass in the steam. No mass was created or destroyed. It simply moved from one phase, water, to steam. Those I'm going to call exchange terms. When bubbles are flowing through a liquid, there's friction at the bubble face with the water. The bubble and the water exchange momentum. No momentum's created or destroyed, it's simply exchanged. There's another set of source terms that I don't know better to describe than acts of God. These are things that come from outside of the control system. For example, gravity. Force on gravity did not come from anywhere in the reactor. It came from outside the domain. Those sources that come from outside, severe accidents. They drive a fire truck up and they pour water into the reactor. That's an external source that didn't come from anywhere in your computational domain. So, we've now covered scalar equations. Now we have one more equation and we're done. Back in freshman physics, you learned that F equals ma. Well, that's all you need. The mass times the acceleration of the velocity is equal to the sum of the forces. If I have a box, the fluid or whatever is in that box accelerates based on the sum of the forces on the box. So we can describe conservation of momentum with that simple box model, which is from F equals ma. We only have two types of forces in the fluid equations. If we go to more exotic things, sodium reactors will have magnetohydrodynamic pumps. So you can get forces on the sodium due to magnetic fields. But, all right, there's three then. But for water reactors, there's just a momentum flux and a pressure gradient. Two forces. And again, we have the same sort of internal and external sources. After you take a step back and you stare long enough at all the heat transfer and friction factors and boiling models, you realize that they all basically take the same form. There is some dimensional part to them that has velocities and densities, whatever units are required to make the source work in the equation you're working in. Then there's another piece, which is often called the closure laws. Heat transfer is Nusselt number equals some function of Prandtl times Reynolds number. These are non-dimensional numbers and relationships between other non-dimensional numbers. That all fits into that term. And then, if I'm exchanging mass, momentum, or energy, if I'm exchanging mass, it's based on the difference between my temperature and the saturation temperature, whether I'm boiling or condensing. If I'm exchanging momentum between two fluids, it's based on the difference in velocity between the two fluids. If I'm exchanging heat between the water and a fuel rod, it's based on the difference between the fuel rod and the water. So, all of these exchange terms take a basic form of a non-dimensional times a dimensional times a driving potential. And the key to these terms is that they only exchange mass, momentum, and energy. They do not create them. So, I needed a scalar conservation equation, a vector conservation equation. I needed exchange terms that connect them, and one term left. And these are linearizations. And since all of my numerical methods in my code are based on first-order Taylor series, I'm going to use a first-order Taylor series to do my. So, an example I showed earlier of a linearization was linearizing density in terms of pressure and temperature. I can linearize friction factor in terms of Reynolds number. But whatever closure relationship I need, I'm going to represent it as a first-order Taylor series instead of a very complicated nonlinear function, because everything else in my code has already assumed a first-order Taylor series. There's a key point that's buried down in here, and this is what is often lost in our current thermal hydraulics codes. For example, I have a friction factor, and it depends on which flow regime I'm in. So, my friction factor depends on the flow regime depends on the volume fraction. But my flow regime is a discontinuous function of my volume fraction. I switch from bubbly to slug flow based on a transition in my void fraction. But if that happens quickly, then my friction factor changes quickly, which means I have a very large error term from my friction factor changing quickly. There's a sad story about this. The French have a thermal hydraulics code called Cathar. And they did a really good job, and they went through and did all of their numerics fully implicit so that their code could take large time steps. And then they left all their closure laws explicit. So the fast timescales, which is boiling and heat transfer, they did that explicit, which made him unstable. And after all of that work, because they missed this piece of physics, they ended up with a very slow code that didn't work very well. So, we have our Taylor series that tells us specific information. Every time I wrote out a Taylor series, I wrote out my approximation and an error term. The idea here is that in our current codes, we set the nodalization and the time step by the code user. So that meant that you, as the code user, were supposed to know all of those Taylor series terms, and you were supposed to choose delta x and delta t to make all of those error terms small. Did anyone tell you you were supposed to do that before they told you to run the code? So the sad thing that happens is nobody knows what they're doing is minimizing those error terms in the Taylor series. So everybody does the same thing. Change the control volume size. The code doesn't run. It doesn't run. Oh, the code runs. There we are. We're going to stop. Well, it ran. Was it giving you a good answer? It ran. The fact that it ran was your definition of quality and accuracy. This is not a good way to define quality and accuracy by does it run or doesn't it run. So we're going to build in processes that quantify and measure the accuracy as the code runs. So this originally sounds like a daunting task. But remember, I only have two equations: scalar conservation and vector conservation. My forces, I only have two fluxes and two forces. I have an advective flux and I have a diffusive flux. The beauty of a diffusive flux is it's already second order accurate. To call that accurate enough. My pressure gradient, because I have a staggered mesh, is already second order accurate. So to control my error in space in my code, I really only have to focus on the momentum flux term and the advective term. So I need to do detailed analysis of the error of the advective fluxes of mass and energy and the momentum flux. Well, one of the things that often gets forgotten is that we write momentum equations that work for very simple straight pipe geometries. But as soon as we run into a pump, a valve, an elbow, any sort of geometry at all in our flow, we put in a loss coefficient. Well, the way you compute the loss coefficient is an experimentalist sat down and he said, okay, I'm going to measure the pressure on this side of the elbow and that side of the elbow. I'm going to raise the velocity, measure it again, raise it, measure it again. So from that, we build tables of loss coefficients. Well, the loss coefficient did not distinguish where the pressure drop came from. The pressure drop came from momentum flux and friction, but it can't distinguish between those. So we lump all of that into the loss coefficient. Well, what that means is most of the time in a thermohydraulics code, there's only two choices for the momentum flux. It's zero or it's wrong. But if it's wrong, hopefully you remove it from the code and you replace it with a loss coefficient. So I got rid of momentum flux, pressure gradient, diffusive fluxes. So if I can do advective flux, I really have pretty good control of all of the spatial error in my code. And internal sources. That's the harder one. That's the one I'm still working on with my students to get detailed analysis on the internal sources. The linearizations, those are trivial to monitor the error because they're based on a Taylor series. All I have to do is use the higher order terms in the Taylor series. So we now are going to construct multiple redundant, independent ways of measuring accuracy. And they're called local truncation. I use a higher order method to measure error, and I compare things to length scales and time scales. So every time I derived a Taylor series, we showed this and the additional error term. That error term is the local truncation term. So I can approximate that partial derivative with this finite difference equation. I can use my local truncation error to give me an accurate measure of how much accuracy I've lost due to my choice of delta x or delta t. This one's a little bit cleverer and a little harder to understand, and I'll explain it to you, and you'll have to go back and think about it and stare at it for a while. But the basic idea here is if I have two discretization methods in my code, one that's first order accurate and one that's second order accurate, I do this basic process. I solve the first order accurate equations. When I solved the first order accurate equations, I got my original PDE plus my truncation term. I substitute that into a second order method, I will get the truncation terms. Because the second order method, the PDE is the same in the first order method and the second order method. So there's a trick I can use to calculate the error directly from the numerical scheme. So in my code, I'm going to build my first order method as a second order method plus an error term. So central differencing is second order accurate. But I'm going to write central differencing plus a derivative. This derivative term is my error term. We can do the exact same thing with our time integration. If we do time integration central in time, it's second order accurate. But our choice of how we represent that derivative tells us our error in time. So I have two input numbers, and based on whether they're 0, 1, or 2, I have two different first order methods or a second order method. But by writing it out this way, I have my error term sitting there, and all I have to do is monitor the term in red, and that tells me the space and time errors in my code. You can also take a step backwards and look at link scales and time scales. These are ideas that I stole from control theory. But the basic idea is the time scale of my physics is proportional to how much it's changing relative to its current value. So, if things are changing slowly, my time scale becomes large. If I'm in steady state, it becomes infinity. If things are changing quickly, then that time scale becomes very small. So I can also step back and just monitor how things are changing in space and time. And if I choose the minimum, so I compute how density is changing in space and time. I compute pressure, velocity, energy in space and time, and I find the fastest changing in time and the fastest changing in space, then I can simply choose my time step to be 10 times smaller than that, which means I'm resolving all the time scales, or my grid spacing to be 10 times smaller than my length scales. What did I just do? If my time scale is a second, and I choose my time step to be 1/10 of a second, that straight line linear approximation of that 1 second curve is very accurate. So this is a way of enforcing that the Tailor series First order Taylor series linearization is accurate. So we have three different methods of being able to control our space and time accuracy. We're not going to have code users guess delta t and delta x and hope that they get something that works. And by carefully constructing my code in terms of control volumes, conservation of scalars, and conservation of vectors, I've really worked accuracy down to a small number of terms. This is the harder concept, and I'm going to do my best to cover this, but this is weird, so kind of stick with me, and we'll try and get through it. The basic idea is this. If I have a room, I can represent this room as a single control volume, and there's 50 people in here, and if I count the number of people that go in and out of the door, I know how many people are in this room. I don't need 100 million control volumes in this room to get the number of people right. I just need to count the number of people at the door. That's a zero-dimensional model. Sometimes it's accurate enough. Or, if there are interesting information, are more people sitting on the right of the room than the left of the room? If that's important to me, then I need to discretize the room and be able to see if there are gradients across the room. But if I don't care about the gradients in the room, I don't need to resolve the information. So, what I'm going to do is start out and say, all right, I'm going to conserve mass, momentum, and energy no matter what. But there's two different ways of writing conservation of mass, momentum, and energy. If I have three cells, I can write a conservation mass equation for each of the three cells. But I can also write a conservation of mass equation for the entire room or a single control volume. The key concept is, and I forgot to mention this, and I apologize. I talked about exchange terms do not create or destroy mass, momentum, or energy. Neither do flux terms. So, if I look at what's fluxing out of cell 1, it's exactly equal to what's fluxing into cell 2. What's fluxing out of cell 2 is exactly what fluxes into cell 3. So, if I add those three equations, the only thing that's left are the fluxes at the boundaries. I only need to know who's going in or out the door. So, by collapsing or summing these equations together, I've made a much simpler model, but that simpler model still conserves mass, momentum, and energy precisely. So, I can now make this a little bit more complicated and work with a concept that I stole from my CFD friends when they do turbulence modeling. The idea is I can represent things as a mean and a perturbation from the mean. This is a standard approach in CFD. So if I look at my densities, I can say how much does my local density vary from the global density in the room. And this gives me a shape function. This one I did steal from my neutronic friends. If you remember back when you did point kinetics in neutronics, you had a shape function that gave you local information. I'm also going to have shape functions. So, what we can do now is I can build a code and carry along two sets of equations. One set of equations for the zero-dimensional model, and that's this one. I need to compute the total density in the room, but through algebraic relations, I can represent the local densities as perturbations from that mean that I'm calculating. Or I can compute local densities from partial differential equations and then compute a total density just by taking an average of those. Now I have two sets of residuals. It may sound initially like I'm doing twice as much work, but there is a difference between using a set of residuals to advance a solution and using a set of residuals to monitor a solution. To advance a solution, you have to build the matrix, solve the matrix, and that's a lot of work. To monitor, all you have to do is evaluate the residual, and that's very cheap and sometimes almost free. So, while I'm running this calculation, if I look at these densities and relative to the mean, they're not changing in time, then I can write out these shape functions and say I'm not going to calculate the local densities from my matrix. I'm going to calculate the total density in my matrix and compute the local densities based on that shape, which is assumed constant. This is the assumption we make in point kinetics. Now, I can run along with this simple model because now I'm only solving one equation. This is going to run very fast. And I'm still computing local densities in each of the three control volumes. I can take these densities computed by perturbations from the mean and stuff them back into these local conservation of mass equations. Now, if these local conservation of mass equations say these algebraic equations are good solutions, I don't need to change anything. But once these equations say there's something wrong and we need to switch, I stop solving the simple equations and switch back to the more complicated equations. By carrying the two sets of equations, I can always use one to measure error and accuracy in the other one. So, I already said that. I'm running out of time, and trust me that the same process. So, what I did for geometry Matryoshka is I wrote residual equations for mass, momentum, and energy, and I summed them together to get mass, momentum, and energy for all the control volumes. Suppose we take Cobra. Cobra has mass, momentum, and energy for droplets, mass, momentum, and energy for liquid, mass, momentum, and energy for steam. If I sum the three mass equations, I get a mixture mass. I know how much mass is in the pipe. I'm not sure whether it's in droplets, liquids, or vapor, but maybe I just don't care. If that is the case, then instead of solving 9 equations, I can add the 3 mass equations to one mass equation. I can add the 3 energy equations to one mixture energy equation, and I can add the 3 momentum equations to one mixture momentum equation. Because remember, the exchanges between masses in those 3 different equations due to boiling, when I add them, it sums to 0. The exchange terms, the friction terms, the wall heat transfer terms, these terms did not create or destroy mass or energy. They simply disappear when you cancel. So, now we're in a very different situation. The fastest timescales in thermal hydraulics come from boiling and condensation. If I sum those equations together, I've removed that fast timescale. If I removed it, my time step doesn't have to resolve it anymore. I can now choose which timescales I want to include in my physics models, and if they're important, I put them in and I resolve them. But if they are unimportant and don't matter, I can sum the equations, remove the timescales, and that piece goes away and my code runs faster. If I have multiple control volumes, I can resolve higher frequency information. If I don't care about the higher frequency information, I can sum those control volumes together and remove that length scale from my calculation. So, with this code construction, we have the ability to choose which physics is important and resolve those length scales and time scales, and which physics is unimportant and remove it. So we are choosing which is important and how, versus the traditional codes now have one physics model, one geometry description, and you get an answer. And sometimes it's too slow and sometimes it's too fast, but you have one, so you have no choice. I'm going to design a code with multiple options so that you have those choices, and based on that, when we need accuracy, we can add physics and resolution and get the accuracy we need. When we need speed, we can remove the length scales and time scales and run fast. So, what I've described is how I'm going to build a code that has multiple length scales and time scales, multiple physics models, and choose and control them. The key to doing this process is not to implement one physics model or one discretization, but many choices of models simultaneously and compare them against each other. I can use geometry Matryoshka to eliminate length scales. I can use physics Matryoshka to remove time scales, but I have monitors for spatial and temporal error around that I can always use to determine whether there's accurate or not. Next time I come back to visit, I'm going to show you results, I promise. But this time, it's how I'm going to build. So last time I told you why I wanted to build the code. This time I told you how I'm going to build the code. Next time I'll show you results. Thank you.
Questions, comments?
I feel obliged to defend the topics against.
All right, good.
So in the equations that you showed, the control volume method is, of course, very well known. The thing is that you do actually solve the differential equation. You need a relationship between outgoing and incoming fluxes, the values of the function, and you do, in your case, you do this by assuming the Tailor series.
Assuming what?
The Tailor series. The Tailor series
Yes.
predicts what's going
Yep.
out to what's coming in. Otherwise, you're going to end up with a system that's not closed. And your big question. What we do in Truncation is we have fancier ways of doing it.
Absolutely. No. And the one that I avoided intentionally was charge particles, where we now have integral long-term collision terms, and hopefully the bear is, in working in severe accidents though, one of my friends reminded me that in the severe accident there are aerosols floating around, and there are fission products attached to those aerosols, and those aerosols all have electric charges. So at some point I might have to get back to my Fokker-Planck equations that I did a long time ago, but for a while I'm going to ignore that. But you're absolutely right. One of the things that's a dirty secret Cord Smith made a bit of money doing neutronics calculations, and the one that I'm not sure how many people know is he used very simple diffusion codes, but he had neutron transport codes that calculated his flux terms for his diffusion code. And that combination of local transport and global diffusion is how he created very fast codes that were very accurate as well.
Other questions or comments?
Question, when showing how you can calculate the time step based on how fast change the physics, the variables, like flux and so on.
This one?
You say that you can assume a time step that is like 10 times less, 10 times smaller than the time scale.
The fastest.
The first derivative. But the error, truncation error, is based on the second derivative, right?
Yes.
Yeah, so it's not a better approximation like base the time step, basing your time step to control the error, so based on like on the second derivative instead of the first derivative?
So, you mean base the time step based on this term?
Second derivative, yes. To control the...
That's my first method.
Okay, so...
So, I will have multiple methods.
Okay.
The challenge here is doing these Taylor series for a few equations. The more equations you do, the harder those Taylor series get to write out. And so being able to write out analytically what that term is, I'm going to do my best to do that, but I'm still going to have two other methods to do the time step control in addition to that one.
I think you mentioned, I don't know if I got this right, but you don't intend to have discontinuities in the models that you use. For example, friction factor, you don't intend to have a different relation or different term somewhere.
Yes.
How do you bridge that gap?
So there's two ways. Nathan's picked up the first one. Explain to him sigmoids.
So you combine them, instead of just having a discontinuity, you multiply them by a smooth function. So one is 1 minus the smooth function and the other is the smooth function. Right, and so the class of functions that you would use are called sigmoids, and so they vary from 0 to 1 smoothly.
That's one approach, which is a more common method. The less sophisticated people just call them ramps. Nathan calls them sigmoid functions. Another approach that I intend to use is if I have a laminar and a turbulent friction, I can write a calculation of how turbulent I think. So I can now advect turbulence and diffuse turbulence and have a source term based on a Reynolds number of. If my Reynolds number is less than 2300, my indicator of turbulence goes down. My surrounding cells are laminar. My indicator of turbulence goes down. And if I was laminar on the last time step, my probability of turbulence goes down. So I can add another partial differential equation that describes my probability of being laminar in terms of and time scales and the surrounding physics. That's the more advanced way to do it.
Other questions? Let's thank the speaker again.
Thank you.
The way you present it is very original, different from other people, I think. It's very consistent.
I've been working on it for 30 years.
And actually connects to most of the things they're doing.
That's what I'm hoping.